Good morning, all. We'll start the lecture number 8, which is on stability of the building frames. To summarize the sessions we have had till now, the session 1, let's say session 0, was on approximate method, importance of that. Session 1 on methods of approximate methods, which are beam reaction method, then total method, then moment distribution method. So three methods are used for the analysis of building frames in 2D. And once that is done, we get the reactions at the base. For symmetrical buildings, these methods are good enough and we can match it with the software. However, when we go towards 3D building analysis, the buildings that are more uh, asymmetric or not having the same load distribution among the frames, the 2D analysis does not give proper results. In that case, we have to go for 3D building analysis. IS 1893 also focuses on or prescribes to use 3D analysis in the software. And the software that we have seen the this demonstration is of ETABS, that is extended three-dimensional building analysis software, and it is most common tool used for building design and analysis. The main significant part of this software is it is finite element based software, and it has more focus on the seismic design of buildings, also dynamic analysis, and the P delta analysis has a good solution incorporated into it, and that is the reason it is a preferred software as compared to other tools. And also for nonlinear analysis, ETABS is a better tool as compared to other softwares. So to summarize, up till now, we have also seen, I had uploaded two sessions last time. That was on the response spectrum method. And also we have seen what is torsional irregularity. It is uploaded on my YouTube channel also, and also uploaded in the MS Teams. So torsional irregularity, how to control it, and response spectrum method, all these are covered. P delta analysis, it is also uploaded on my YouTube channel. You can also go through that session. Considering all these aspects, we are, just right now doing on the analysis part of it, because analysis part is the first framework into which you get the preliminary sizes, also stability of the frame, loads, load combinations. Uh, First step starts with understanding of the building geometry and also what loads are coming onto it. Once you have noted it down that what are the list of loads coming, which is dead load, super dead load, live load. In live load, there is lift load also. Then there is a area parking load. So in that case, all these loads that we get, apart from the earthquake and the wind load, these are critical for gravity load analysis. And so gravity plus lateral load analysis, total, you have to estimate the forces. And based on the combination of the forces, then we design the structure. So analysis is very critical, and you should have grip on that manual methods as well as the software utilization. So that was the main focus till now, to gear you up on the fundamentals of structural analysis used for high-rise building. And I had shared textbooks also on that part, but many people have not yet taken this seriously. And that is the reason we have not had sessions last two times. And I think Akhilesh has shared the model of the building I had given for modeling in ETABS. However, the section sizes are not the same. However, the geometry has been modeled correctly, but section sizes are not there. So we cannot use it for analysis. So section sizes have to be properly done floor wise. Otherwise, we cannot use that model for analysis. So Akhilesh, have you updated the model to real section sizes, or this is the last status that you shared with me?
Sir, I have not updated yet. Today I will do that.
Okay. So Srinivas, have you done anything on that? T-types modeling?
Sir, I am trying to done it and I form the grid of the whole building, but when it comes to sections, there are too many sections, right? Sir? So very that which I feel it's too complicated, and I'm trying to do it.
So no need to model each and every element as it is. Take a section size which is at the ground floor and use it for the full height. Then you can optimize it later and you can come to that conclusion that, what size is required as per that. So all ground floor column sizes, wall sizes, beam sizes, you can incorporate till the uh, full height of the building, right? So you make one story, replicate it, and close the model. Okay.
Okay, sir, okay.
So this way you can start modeling. You can model this building because optimization is the next part. First is you replicate all the frame sizes on the ground floor and take it till the top floor. Okay, so that will make it easier, right?
Yes, sir.
So that way you could have asked me that what to do. So I could have also replied it in the group that sizes are optimized, but modeling can be done for initial analysis. You can do the same size as ground floor. Okay, so when you complete it, let me know because once you have modeled the grids, all this becomes very easy. You have to maintain the offset. The first and the foremost importance in modeling is you have to follow the wall center line, or let's say beam center line, because beams are and walls are always aligned. So either so in analysis, you should take beam center line. Okay, architect takes the wall center line, you have to take the beam center line. So all your modeling has to be done as a center line model. All that center line is of the beam. If the column has an offset, you have to model that offset in the column or shear wall or whatever element is there, offset has to be done. But beams are always center line in that particular case. So all mean beams, center line modeling has to be done. And with respect to that, grids are created, and with respect to that, the columns and beams are placed in the model. So I think that is one important part of it that all should know before modeling in the software, that how to model it and a plan when architect gives to you, how will you generate a model from it? That is the first step to it. You draw the beam center lines, which may be because if they are showing you only the walls, so in that case you will take the wall as a center line. So all those important parameters you have to see that how are you going to size it and which center line you are going to follow in your model. So today's session is dedicated on the stability of the building frame. So building frame is overall stability. Then there is local stability of the columns and walls. that is a separate thing. Overall stability, we take into consideration the drift and P delta effect. So drift is what is the definition of the drift? What is the definition of drift index? Then what is stability and how it is ensured in the IS code? So which parameter is important in IS code related to stability? That is what we have to also we'll come to know from this exercise. I'll switch off the camera. So this is the chapter number 7 from the Handbook of Seismic Design by Dr. Farzad Naeem. This is a very important handbook. You should refer this entire handbook. I am just projecting the chapter number 7, that is for the drift and lateral stability. And we have to design for the stability and we have to design for the drift. So in our IS code, there is a drift ratio 0.004 of the story height, that is 0.4% drift. Now this 0.4% drift is for what reason that we should know, because our elastic stability is related to this index. However, when the earthquake happens, this elastic stability, we are going beyond this drift limit, that may be around 1.5%. Then also the building does not fail due to instability, it fails due to failure of the individual element, not as a whole structure, that the element has failed due to some let's say gravity load or lateral load, not like that. As a unit, it is behaving, the whole building is behaving as a unit, and it is trying to give resistance to the earthquake force, which is generated by the ground motion of the earthquake in cyclic nature. And in by going in the cyclic nature, it has energy dissipation, and these deformations are captured in form of the response reduction factor R, in which important is the ductility. So higher deformations, the structure is able to take up to 1.5% drift before failure, as compared to the elastic drift of 0.4%, which is related to the elastic instability. So instability in two aspects, I have explained you that how it is understood in the lateral forces. Under the gravity load, what happens? There is a critical load, PCR. Now this PCR is related to what? Now, as the axial force increases on the column, if it is a pure axial force on the column, initially the load is, let's say, 0, and slowly it is increasing at a constant rate. Then at some point the column will start bending due to the axial load, and as the force increases beyond the that capacity, it will buckle. Now this buckling will related to PCR, which is the we know that PCR is obtained using the end restraints, that what is the end condition of the column, and also on top what is the end condition. And based on that, if it is a fixed, whether it is a pin, based on that we estimate the critical load onto the column. And do you know what is who developed this principle of the critical load for the column?
Euler.
So Euler buckling load, okay, that is what we call. So from this, we estimate whether the column is stable or not. Or let's say buckling has to be restrained, so it should not be buckling. Should be not be that is one of the failure criteria, and we should restrict the column from buckling. So we get the PCR value, and this PCR value is a bifurcation point, because any lateral load which is going to apply after application of the critical load onto the column in the axial direction, the column will will shift from its stable position and will become unstable. So due to any lateral load after application of the critical axial load, the column will become totally unstable. So there is a bifurcation load. We call it a PCR. So PCR is equal to the bifurcation point, wherein when any lateral force will apply or any increase in the axial load also, there will be a lateral displacement, and that will lead to unstable condition of the column. Right. So that is due to the gravity load PCR, after which the column can become unstable either due to any application of the small lateral load or any increase in the axial force, which will lead to, lateral displacement into the column. Due to the axial load also, the column may displace from its position in the lateral direction. So that is a small delta. This small delta is related to individual column which has a double curvature. So when column has a double curvature, it has a small delta associated to it. So that is a element delta. So that is a local stability. Now, when we look into the overall picture, we get a capital delta. Let's say there is a pinned connection at the bottom of the column and lateral load is applied. It will not have a double curvature. It will have single curvature only. And this will give us a total delta in the column. When the base is fixed, you will get double curvature. When the base is pinned, you will get a single curvature. And similar to that, you will get small p delta into the column and also the capital P delta into the column. So due to the increase in the gravity load and application of the lateral load, this is a sway frame. So when the frame becomes a sway frame, why we call it a sway frame? Because we don't know after application of the how much vertical load, okay, and the lateral load combination, this sway will, the frame will come in the sway condition. As per IS 456-2000, it is told that P into delta divided by lateral, let's say story shear V into story height H. This is a ratio P delta divided by story shear into height. So this ratio should be less than 0.004, sorry, 0.04. Now, if this ratio is not less than 0.04, then the frame is a sway frame as with respect to that particular condition. So at every story, you will have to find a P, you have to find a delta, and you have to find what is the lateral force and what is the story height H. And from that, you have to estimate whether this story is having a sway or not, or what. So it is a sway frame or not a sway frame. At inter-story level, also you'll have to find as compared to the full condition as well. So basically, all frames are, when you consider the earthquake force and the wind force, have to be considered as a sway frame in general. And these sway frames have a different, criteria to uh, satisfy for all these aspects as mentioned in our codes and the textbooks. So this is the important part, that what is the interstory drift, what is the total drift, and what is the stability condition of frame, whether it is a sway frame or a non-sway frame, and how to analyze this particular frame is of the particular importance in analysis. So that is the focal point of this session today. Now, if you see this particular screen, this in this particular screen, there is a frame that has been drawn, and lateral sway of this frame has been shown from top to bottom, and it is a fixed at base. So you will see a double curvature in the column. So this double curvature is seen in all columns. Okay. And also in the beam. So beam also has a double curvature, column also has a double curvature. And at story 1, there is delta 1. Then there is delta I minus 1, delta I. So basically, this is delta 1, or you can say delta I. So delta 1, delta 2 up to delta n is there. Now at top position, it is delta I, and here it is delta I minus 1. So this is, let's say, second story and first story. So delta 2 and delta 1. So delta 2 minus delta 1 is the relative displacement of the story. That is what we have to obtain. So delta 2 minus delta 1, we will give you the particular story drift. And top is total delta. So combination of the displacement at each floor is delta total. So you can say overall drift or the displacement is delta top. Okay. Story height is hi. Now inter-story drift is what any story and that is displacement of story n minus displacement of the story below it. So n minus 1 or delta I minus delta I minus 1. So delta 2 minus delta 1. So that would be interstory drift for delta 2. That way you have to estimate for each story what is the interstory drift, and this is how the software also calculates it. And overall drift index. Now what is the meaning of the drift index in total? So delta top, that is the total displacement upon total height of the building. It is the drift index overall. Interstory drift index is more critical, which is equal to delta I minus delta I minus 1 upon story height. So any interstory drift divided by story height will give you interstory drift index. Now these are the definition of the drift as for the building frames, how we estimate it. So why do we need a drift-based design? Because number one, due to earthquake and the wind, the lateral displacement of drift is very critical, and it affects the structural stability. Also, it affects the integrity of the structure, and potential damage to various non-structural components can happen. So, we want to avoid damage to the structural and the non-structural components both. And third, it affects the human comfort. So in high-rise buildings or let's say tall buildings that are slender in nature, we have to give special focus to the comfort of the occupants. So up to let's say 40-story buildings, we are okay. But beyond that, we have to give special focus to human comfort. And in any slender building also, we have to give a focus on the human comfort. Otherwise, people will feel dizzy on the top stories. So that these are the three critical parts based on which we have to design for the drift or displacement for lateral loads. Now you can go through this entire document. I will upload it in MS Teams. Okay. And what is structural stability and what are the index for it? Like 1.5% structural damage will happen. 0.7% non-structural damage and some structural damage will happen. So that way many categorizations are done, that what drift ratio, what will happen to the building, and what should be our limiting displacement as per IS 456.4%. We have to limit the interstory drift. Otherwise, non-structural damage will happen to the building components. So that way 0.4% has come into our IS code. Now, human comfort is motion susceptibility, and wind-induced oscillations are mostly the reason for this, continuous discomfort to the occupant, because earthquake may happen once in a lifetime or twice in a lifetime, or may happen some intervals, but wind is always there. So that may lead to continuous discomfort to the occupants, and for that we have to employ different aspects like dampers or higher stiffness, bracings. All those things have to be taken into picture very seriously. So this comes into picture in very high rise buildings, or let's say any building which is more than 30-40 story, and all buildings that are slender in nature. So this is what I explained to you regarding the critical load. Also, you can go through this document in detail, that initial displacement of the column due to axial load, slowly it is increasing, and then up to the failure. So graph is in the reverse order. This is a perfect column. This is for the column with slight imperfection. Okay. So this way you will get the graph for P upon PCR. So P upon PCR when it is equal to 1, this is the condition. So this is first a straight line. Okay. So everything is a straight line in the initial case. When the P becomes more than PCR, then this graph is generated and finally the collapse will happen. So this way, this nonlinear graph for axial failure of the column is there. Now, second case is related to gravity load is constant and horizontal load is there. So there will be a negative slope after the yield point. Okay. So this goes into the cyclic nature, and this is the reason the building is able to survive the earthquake and does not seem to be unstable even when the deformations are very high level, because we have a negative slope graph which has higher capacity as compared to the initial curvature. So that we are representing also ductility. So delta ultimate upon delta yield. So how much this ratio is more inelastic deformations it can resist and be stable and intact during the earthquake. So this is important, that exact computation of the critical loads, that is the axial load, for real buildings is a formidable task. This is true even in a static environment, let alone the dynamic loading and the inelastic response. Exact buckling analysis is beyond the capacity and resources of a typical design office and beyond the usual budget and time frame allocated for structural analysis of buildings. So in the dearth of the time and resources, we are not able to exactly analyze each and every component, and hence we are not able to reach a exact deformation criteria for each building. So in that case, how we should ensure that minimum criteria is met and for which the code has specified 0.4% drift limit. So in everyday structural analysis, the stability effects are accounted for either by addressing the problem at the element level, that is via effective length factor. So step structural analysis, we consider the effective length factors, or by application of P delta methods, we are addressing the stability effects. And the simplest way to minimize the lateral stability problem is to limit the expected lateral displacement or drift of the structure. So what is the best way to restrict the drift of the structure? So in several studies, it has shown that by increasing the lateral stiffness, the critical load of the building will increase. So we don't have to depend on estimation of the critical load. We indirectly hint that if you keep this much stiffness in the building, then critical load effects will be countered, and the chances of the stability problems will get reduced. And drift limitations are imposed by seismic design codes primarily to serve this particular purpose. So now we know that why drift limitations are given in the IS code. And if we want to go beyond that, then we have to do more accurate analysis on the buckling as well as P delta analysis we have to do. So you can see there is a P delta effect in which lateral load is there. This is the gravity load. This is the top moment, bottom moment, lateral load and gravity load. And column is in double curvature. And if the column were to be straight, this is shown in the dotted line. So they have divided the first diagram into two parts. One is inclined column. You can see it here. Okay, this inclined column is a strut model, and this deformed model is given. Now P into delta by L. So previously you had seen column was straight, and now there is some delta. That's why the column has moved to a different position. So there will be a P into delta. So moment is P into delta by L. So this is the lever arm and these are the moments. So P into delta by L will give you the moment at top, and P is the axial force and V is the shear force. Now this is the actual condition of the column. Instead of the straight condition, now it has a moment which is P into delta by L. So axial load and lateral load were already there. Now due to the displacement delta, that is the addition of the moment P into delta by L at the top, and in the reverse direction P into delta by L at the bottom. So a couple is created to represent the moment M top and M bottom. P into delta by L is added into the frame. That is into the column. You can see that. So additional moment has got added into this element. Now P delta effect, P delta by L, and this is the column and strut effect, that is the axial force. So that is a combination of the two. That is major second order effects. So this distance between dotted line and curvature, this inclined portion, if you my cursor is visible to you, there is a dotted line and there is a this solid line in curvature. So distance between dotted line and solid line is small delta, and at the top it is capital delta. So this is a small delta effect and this is a capital delta effect. Both are the two effects that are captured, and major second order effects are represented in front of it. So in case of the gravity and the lateral load frame, this is the deformed shape and these are the P delta effect coming onto this sway frame. I hope it is clear what I am trying to convey to you. Now this is the case one in which there is a shear force at point B and axial force at point B. So what is the reaction? V equal to VA, and moment at A is equals to V into height of the column. Now if I give a delta 1, then what will happen that it is at the deformed position. So my lateral force will now act in a deformed position, not in the vertical position. So previously, when I was considering the column to be straight, my moment was coming out to be V into H. However, due to P delta effect, the column has moved to a new position, which is a delta 1 distance away from original position. So I will apply the load V and load P, okay, at point B, which is now shifted by delta 1. So every load remains the same except the position of the column has changed due to P delta effect, and initially delta 1 position has achieved. So this is what we are doing in the software also. In the preset P delta option, we are giving 1.2 times the dead load plus 0.5 times the live load. This is the similar situation we are doing in the software. So we are moving the column a bit and then applying the loads and doing the analysis after that. Okay, so this is what will happen. Base shear will remain the same or the shear will remain the same, V equal to V. However, moment A will be equal to V into H plus P into delta 1. So P into delta 1 is the moment here. So P into delta 1 moment is added. Now this is due to what? This is due to your movement of the position of the top of the column. So this is due to lateral load. Now due to the axial load also there is a curvature in the column. So due to the local curvature or the bending of the column, there is again a delta 2. So you will get V into H plus P into delta 1 plus delta 2. So this second order effects, P into delta 1 plus delta 2 is getting added into your frame by movement of the position of the column from initial vertical position and also bending of the column due to the axial loads. So this way, what has been shown here, so this is change in position and this is your axial forces. So when your small delta generated due to axial force, due to lateral force, capital delta got generated. So P delta by L plus P into delta small. That will give you the total second order effect. So all these two effect has to be considered in all frames that we are analyzing for the lateral forces. So we are analyzing the building in a deformed condition. That deformed condition has occurred due to application of the sway frame, considering the frame to be sway, that it the due to application of the gravity load, the frame is moving by small delta. Sorry, is moving by delta, and small delta is for the column. So hope this concept is now clear to you. What is P delta and how it is getting generated into our frames and how we are analyzing it in the software also, and also how manually to consider it. So there is a full, frame analysis done by the author for this steel building along with a concrete core, and P delta analysis with P delta, without P delta, what it is coming has been estimated. So before going that, there is important point that what are the factors that are affecting the lateral stability. So one is the rotation at the base of the building. Okay, so what if the base is fixed, it will have very less rotation. If it is pinned, it will have high rotation. So the stability is dependent upon the whether the frame is fixed or pinned. Now during the earthquake, in the elastic case, we had considered the base to be fixed. But if the base the column at the base has yielded, then it will act as a pin connection. And when the hinges form at the base of the building, that is when the stability will slowly try to lose, because the stiff condition has now become a flexible condition, which is a pin connection in which the rotation is free. And in that case, the building will start swaying more and it will undergo heavy damage. So in those cases, the stability start to go away from the building. That's why in performance-based design, when we do the pushover analysis, we consider that at the base of the building, it is okay if it is yielding, because we cannot control that yielding. Apart from that, any yielding of the column at the base in above stories are prevented. So at the top and the bottom story, we cannot prevent the software from generating the hinges. However, in between, at each story bottom, the hinges should not form. That is the criteria, best criteria, or the ideal situation that we assume for pushover analysis. So one is the plastic hinge formation or rotation at the base. That is a very important parameter that significantly affects the stability. Also, asymmetry or torsion in the structure also leads to reduction in the stability, because in 2D frame or the 3D building or 3D frame, uh, we consider X and Y direction. If there is a third direction in which there is a rotation, then due to these additional forces and rotation of the building, the stability of the building reduces. That's why the torsion mode has been kept at the third mode, so that it has more capacity to resist the earthquake in X and Y direction. And after that, it should, take the be more sensitive to the torsion. Otherwise, it will have less stability and less resistance to the earthquake forces. Now, there are various methods by which the second order analysis can be carried out, P delta analysis. So this was the basic understanding on P delta analysis on the drift limitations or the requirements of the building for these waveframes. Now there are various methods by which we can solve the problem. And the effective length factor method is method 1. However, I'll not go into depth. You can go into depth for this for understanding purpose only, because in the software we are not using this. However, there is a difference in P delta analysis method in STAAD and ETABS that I will just mention here. So for the sideway prevented case, so GA, that is the shear modulus of A and B. Okay. So if it is A and B, then there is a braced frame. So grid A and grid B divided by 4 pi square upon k square plus GA plus GB by 2 1 minus pi by k 10 pi by k plus 2 pi by k 10. So it is taken from Euler formulation. That is what you can see, in which pi is taken more. That is equal to 1. Then the sideway will get prevented. And for the sideway permitted case, it is equal to 0, where G and GLB are the relative torsional stiffness of the beam to the columns measured at the ends A and B of the column under consideration. Now G is equals to what? Sigma of IC upon length of column, I G upon length of column again. I think it is beam. It should be I beam. Okay. So column upon beam, if the length are same, then IC upon IB, it will be the case. So this way, you've obtained the relative stiffness of the beam and column. And from that, this whole equation will form. K will be the stiffness of the, let's say, effective length factor. So it will govern the stiffness. That is, effective length factor is 0.5 or 1 or 1.5 or 2, whatever it is. So K into L is the effective length of the column. So this should be equal to 1 or it should be equal to 0. From that, you will obtain whether it is sideway permitted case or it is prevented case. So mostly it is depend upon relative stiffness of the column on both sides of the beam. So in this method, if a stability failure is to occur, the entire story must fail as a unit. Example and evidence of the shortcomings of the effective length factor method have been documented by McGregor and Haig. So they have done analysis for the tall buildings, and they have suggested this method is not accurate enough, and hence we are not following this method. Now approximate buckling analysis, that is also not going to give us the good result. That's why we are not following it. However, for interest, you should read through this document. So buildings are modeled at flexure cantilevers, and from that the critical loading are estimated, and from buckling estimations are done. However, this is never true. So we will not consider this method at all. So one is related to So what ETABS is considering, it is considering the iterative method. However, what STAAD is considering, I have to see approximate P delta analysis. These methods for approximate P delta presented in this section, P delta by iterative method. direct. So this direct P delta method is applied by StatPro. However, the ETABS has option for the two, but we mostly use the iterative based method. And negative bracing member method. So three methods of analysis we are going to see because these three are only used. So if we go by iterative method, in this method, the iterative P delta method is based on the simple idea of correcting the first order displacement by adding the P delta shear to the applied story shear. So whenever we are doing the displacement without the P delta consideration, that is without deformation of the frame, the column is straight, and when we are analyzing it, that is the first order displacement. Now, what is the second order displacement? When we apply the displacement of the frame, column is shifted from point A to point B, and then we do the analysis. That is the condition. Second order we are considering. First order, column is straight, and we are analyzing it. So we add the P delta shear to the applied story shear. So moment is converted into a shear, and then it is applied for each story. So we calculated shear V for let's say story 1. Then after applying the P delta moment, we obtained the shear. Then we add it to that story. So V plus delta V, we got a new story V1 at story 1. So that is iterative based method in which we first do the initial run with straight, and then we add the P delta story shear into story shear. Now, since P delta effects are cumulative in nature, this correction and subsequent reanalysis should be performed iteratively until convergence is achieved. Basically, the second order or P delta analysis is elastic analysis only. It is not nonlinear analysis, so it does not have a material effect onto the building. And hence, superposition is possible. So this by principle of superposition, we can analyze it and add the values simultaneously. So after rerun of the analysis till we reach the solution is there is a in the software there is a solution incorporated into it, that is a coding in which we give the accuracy of the result. So till we don't reach that accurate analysis point, the software will rerun P delta analysis and till that accuracy is obtained. So all those things can be added and final results can be obtained. Okay, so by in the that P delta analysis is also elastic analysis only. However, it gives the second order effect in which there is a geometric nonlinearity. Geometric nonlinearity, that means it is moving from one initial position to a second position due to the sway. So I hope whatever I am saying, conveying is making sense to you. So any query till now? So if there is no query, I'll continue. Now, at each cycle of iteration, a modified set of the story shears are defined as, so Vi, what we want to obtain, that is equal to sigma of V1 initial run plus P in sigma of P into delta of I minus 1 upon H. So what is happening at story 1, we have the shear 1. Now let's say I am doing for shear story 2. So Vi, now I make it V2. Then this will be V1 plus P into delta of I minus 1 divided by H. So my story 1 delta into P divided by H, I will add to this story. Okay, so I will get a story for story 1 also I will get. So delta I minus 1 is equal to 0. So sigma for V1 equal to V1. For V2 it is V1 plus sigma P delta I minus 1 divided by H. So this way I will keep on iterating it. At each story I will find the lateral force and software is also going by this method only in iterative P delta method in ETABS. Now, sigma Vi is the modified story shear at the end of the ith cycle of iteration. Sigma V1 is the first order story shear. So this is V1 is what? First order story shear. Now, first order story shear will obtain at each story also. The first order story shear you will obtain, and this is the second order story shear you will add. So first order story shear plus second order story shear, total story shear. So okay, we will not get accurate story shear because of the approximate nature of all these methods that we are going to see for P delta analysis, but we are okay with that. And we go ahead with this particular problem. So you can see the building that I had shown you previously, the 10-story building, which has been analyzed as steel building with the central core. Story height is 144 inches. Bottom story height is 180 inches. Gravity load at each story, it has been obtained. Now it is sigma p, not p. So what is the story at top plus story plus story? So it is the total story. The total weight of each story has been estimated. So if you take sigma w in kilonewton, then top story plus 9 plus 8 plus 7 6 5 4 3 2 1. You add total, you will get the total seismic weight of the building here. So this is the sigma w. Now lateral load, that is the QI that we estimate as per IS 1893. So from VB, you obtain the VI, or you can say QI at each story, whatever the force is coming, you will get this. So this is part of the linear analysis, or this is part of the first order analysis that we estimate. So this will give us V1. So your V1 is story shear, and this is total of the story shear would be like 30 plus 21, it was 52, and plus 19 plus 17. So you will get the total story shear at the bottom. Okay. So this is the added seismic, added lateral load. This is the lateral load, and this is the lateral displacement. So first order analysis, you get some displacement of the building to obtain that displacement. And this is the story drift delta 1. So same you have to create a Excel sheet in your any system. Okay. And from that story drift, you can find out from this displacement 7.996 minus 7.479 inches, you will get 0.517. Same, you can just obtain the story drift. So delta I minus 1. So that will give this minus this minus this. So 3.2 minus 2.4, 4.1 minus 3.2, 5 minus 4.1, 5.5, 5.9 minus 5. So it will be 0.907. So that way you will get the story drift as per definition mentioned above in the first page. So you got the story drift. So this table got generated for the frame building. So P delta contribution to the story shear is sigma P. So sigma P you have got, delta 1 is your story drift divided by story height. So now 612 is my sigma P. Now 612 is for the 8th story. Okay. Delta 1 for the 8th story is equal to 0.785 divided by height of the story is 144. So this much kilonewton of the story shear you will get. And what you will do, 71 0.74 was the V1, that is the first order story, plus 3.34. Now this KIPS, you may consider kilonewton. You to it, you will get the story shear. So how much percentage of story shear is added? You can see from this calculation, that is 3.34 divided by 71.74. So 5% story shear got added due to this particular arrangement of the building. So what stiffness you have provided to the building? What are the column sizes, beam sizes? So how much stiffness you have provided, based on that, the second order also will get generated. So based on delta 1, that is the story drift, you will get an additional shear, you will add it and you will find the story shear for it. Now repeating this operation for all story results in a modified set of story shears from which a modified set of applied lateral load is obtained. A new first order analysis of the frame subjected to these modified lateral loads results in a modified set of lateral displacement and story drift. So D2 and delta 2 represents the displacement after second order effect and your drift after second order effect. So now the maximum displacement obtained from the second order analysis was 8.478 inches. I think it has been mentioned here somewhere, 8.478 inches. This is the modified displacement. Now how it is obtained, that we'll see. So from this table, now we are going towards the another table. In this 7.996 inch was the displacement. Now you can see all the displacements have changed, modified lateral displacement. So what has been done, that sigma p delta 1 divided by h, okay, that we had seen here, sigma p delta 1 divided by h for each story is obtained. So next table is created. Now first order shear plus second order shear is added and total is done at the bottom. So 151.34 versus your 142.31. So it is 9 kilonewton something is added, or KIPS. Now modified lateral force is you had obtained for each case. So that is also there. Now modified lateral displacement. So how do you get this modified lateral displacement? So as the force has increased, the displacement will also increase, right? So whenever you will consider this lateral force with 5% higher lateral load, there will be some increase in the displacement also. So let's say 7.996 divided by 8.478. So 6% increase in the displacement. So round about 5% increase in the story shear, 6% increase in the displacement has taken place. And you can see the maximum displacement obtained from second order was this, which is 9% larger than the original first order displacement. I don't know why it is saying 9%, but if the displacement is 7.996 and 8.478, then it is to be 6% of the displacement. Okay, so that way you will get higher displacement due to application of the higher load into that analysis. So you have to rerun the analysis and you have to find out the new displacement values and you have to keep it here. And again, you get the story drift, that is delta 2. So that is the iteration number 2, first cycle of iteration. Now I should also consider more cycles of analysis to be more exact. That is why I am doing it again. I am doing sigma p delta 2 divided by h sigma V2, that is from first order, first cycle. Now second cycle, sigma P delta 2 by H. Again, I am improving. So modified lateral force 30.87 become 30.89. Till this iteration does not coincide to 0.001 in the software, I will continue. So you can say that 30.89 should happen again. Then I will stop the cycle of analysis. And after doing all those things again, I get a new displacement from 8.508, 8.510. So all these changes you can see has happened. And the story drift 0.533, it has become 534. So nominal change in the story drift also happened. There is only 1% displacement change happening. So that's why we have stopped the analysis after the second run. And we can say this table is final for the story shear and the displacement and the drift condition. So your story drift, your displacement and drift has to be concluded. Because only 1% difference is now coming from iteration 1 to iteration 2. So first order and second order lateral displacement and story drifts are shown in the figure. As indicated by this figure, the results are virtually identical to the exact results. So this is only one method. I'll go through. Other method you can go through and you can ask your doubt if it is significant to you. Okay. So all these methods have been shown, and based on the example, the values are also taken and problem is also solved. Now exact P delta analysis, construction of the geometric stiffness matrix. So geometric stiffness matrix is the backbone of any exact second order analysis. This same matrix is also essential for any finite element buckling analysis procedure. In this section, the concept of geometric stiffness matrix is introduced and a general approach to exact second order structural analysis is discussed. Now we know from the slope deflection method 4 theta at point where the rotation is considered and the point that is away from it plus 2 theta minus 6 delta by L plus 6 delta bottom by L. Okay, top and bottom EI by L. So that way it has been drawn, this equation. Now for force equilibrium, minus of m top plus m bottom by L minus P into delta top minus delta bottom by L should be equal to Ft and Fb equal to minus of Ft. So this is the moment due to fixed condition and this is moment due to P delta condition. So fixed end moment and P delta moment. Now substituting the equation, you will get what? Minus of 6 EI theta by L square. Now this is due to the shear force. This is due to the moment plus 12 EI by L cube. So my 6 EI theta by L square is now becoming 6 EI by L square theta top plus theta bottom plus 12 into EI by L cube now becomes 12 EI by L cube minus P divided by L into delta. So all these are moments. So 12 EI by L cube is a moment and this you can see P top minus bottom, okay, into P is a P delta effect. So 12 EI by L cube minus of P by L, delta top minus delta bottom. Now this has become a new equation to be solved for the considering the stiffness of the building. So now this stiffness formula, stiffness matrix will change. So moment top bottom Ft Fb is equal to 4 EI by L, 4 EI by L and 2 EI by L. So 4 EI by L, 2 EI by L, and this is 4 EI by L minus 6 EI by L square, 6 EI by L square. Okay. So this is not changing due to the moment. Nothing is changing. However, due to the force, the change you can see is minus 6 EI by L square. It is symmetric. Minus 6 EI by L square. It is again symmetric. However, there is a change in this particular part. 12 EI by L cube minus P by L minus of 12 EI by L cube plus P by L Now this is symmetric, so minus 12 EI by L cube plus P by L, and this remains the same, 12 EI by L cube minus P by L. So theta, theta, delta, delta. So what is related to this moment and delta? That stiffness has to be modified. Shear and delta will not happen. Moment and delta, there is a change in the stiffness equation. So this stiffness equation has to be applied, and you can also apply to a particular frame, and also you can see how to take this forward. And you can create your own coding and check the changes that happen into the stiffness formulation. What is there? Is it matching with the software or not? Okay, so this has been given here, which has to be applied into your particular problem and checked. So first order stiffness matrix, material matrix, and Kg is the geometric stiffness matrix. So you can see the stiffness is reducing. So if you had not considered the geometric nonlinearity, you would have considered Kf, which would have been quite high as compared to the current K, which is having substitution from Kg. So Kf minus Kg is stiffness matrix. And Kg is the geometric stiffness matrix given by all other 0, that is 1, 2, 3, 4, 4 by 4 matrix, plus B by L and minus B by L values. Okay. So this is getting reduced. So stiffness is getting reduced due to second order effect. So that is the reason we are getting the higher displacement also. So this is the entire, generation of the matrix. Geometric stiffness matrix for three-dimensional rigid diaphragm building, how it is to be obtained. So alpha 1 0 0 eta 1, alpha 1 0 0 eta 1, beta 1 0 0 eta 1, alpha 2, and beta 2. So this way, this is very, in general, it has been written. If you go into more depth of it, so x1 y1 r1, x2 y2 r2, right? So rotation and x1 y1 displacement in 1 and x2 y2 r2, that is displacement and rotation. So this is xi yi ri xi plus 1 yi plus 1 ri plus 1. So this is from member 1 to member 2 and then all other members. So this way it will keep on adding and total matrix will get generated. So after you generate this matrix, you can also run your own program, and the software should match with respect to that also. So this rest of the thing you can go through, and this cantilever displacement is important for high-rise buildings or slender buildings, in which you can see the bending moment on the perimeter of the frame, right? We were assuming that all columns will have equal, axial stresses. So this is the axial force diagram, and however, you see that due to the effect of the lateral force, the end column have higher axial force. Okay, shown by dotted line. So this curvature 1 is the real representation of the axial forces. And if we consider this uniform distribution of the axial forces, then the columns will fail or the frame will sway and it will have high instability. And to avoid this, we are also having the elevation bracings on the building. So many buildings that you see, the diagrid system is there. So cross bracing on the facade of the building is visible. Front, all sides of the building, the bracings are visible along many stories, like 3-story bracing is there. cross bracings are provided or single direction bracings are provided. This is done to reduce the axial stresses on the column. Tube-in-tube system for the high-rise buildings also does the same way. So all these are made by Dr. Fazlur Rahman, and I will upload one session of mine on diaphragm. This what we call it high tall buildings. How to understand for it. I'll upload it in the MS Teams, another session that I had taken for one of the universities. So I will upload it in MS Teams. You go through that also, so you will get understanding on other parts, backstay effect. Also, you will get understanding on this what we say codal provisions for high-rise buildings and aspect ratio and all these things for the high-rise buildings. So this is not like in one lecture we cannot cover everything, but this is full analysis provided for one small example. So the step one is to compute the story moment of inertia. Now, what is the story moment of inertia? Like for entire story, what is the moment of inertia? Using equation 7.45. So ACI into DI square. And if we see ACI is the cross-sectional area of the individual column in the entire floor, and DI is the distance from center line of the frame. So from center line of the frame, each column, how much it is away, that is like AH square that we had. So area of the column into H square. All columns you have to do at the center of the building, CG of the building, and you have to obtain moment of inertia I, and compute overturning moment, whatever the moment is leading to its overturning. Compute the area under M over EI. So area under M over EI is equals to MI plus MI plus 1 into story height divided by 2 times E into I of the, that is moment of inertia of story I. So whatever story 2 is there, so moment 2 plus moment 3 into H2 upon 2 times E into I of the story 2. You will get for A2. So area you obtained, then you compute the xi bar from this equation. So hi by 3 mi plus 2 mi plus 1 upon mi plus 1, you will get the what we say centroid, and you compute the story displacement delta ci is ai into hi minus xi bar sigma a into hi minus xj bar. So xi bar and xj bar, you can see hi is the total height of the ith floor. So this is floor height, capital. Total height of the ith floor from the base of the structure. So from the bottom, whatever the floor is there, you will get that height, and hi is the story height. So this is like I1, I2 up to that IN, and this is your 1, 2, 3 up to number of floors. You will get a centroid this way. A distribution is there. Now you will get the displacement using x1 bar, x2 bar, x3 bar. All those things are there. So you will get delta 1, delta 2, delta 3. Now, how estimating the cantilever displacement by the moment area method. So using moment area method also, you can obtain the displacement, and this is applicable to slender buildings, let's say tall buildings, not even high rise, tall buildings and buildings that are mostly controlled by flexure, very high rise buildings. So in which the cantilever method is possible, in that case, you can use this moment area method to estimate the displacement of the building. So these are all approximate methods to estimate the displacement based on moment of inertia calculated at each floor. So all these are manual methods to do all these things. Now there is shear leak displacement. In buildings with closely spaced columns and deep girders like tube in tube, such as framed tubes, the contribution of the shearing deformations to the lateral displacement, called the shear leak effect, may be significant. So there is a new term called the shear leak effect, in which the contribution of shearing deformation to lateral displacement may be significant. So these beams are governed by shear rather than flexure, and this is what has been represented as shear leak effect. And drift due to the shear leak effect may be estimated using this formula. Okay, so I don't want to confuse on the frames that we are doing versus this. However, this concept is important, but how to apply it, you will have to go more deeper into it. So you also read through it and you can ask your doubts on this particular topic. What is the shear leak effect and how it is affecting the displacement of the building. So shear modulus and AGI and ACI are the shear areas of individual girders and columns at level I. And I effective you will obtain and you will get the displacement. Then another is the panel zone distortion, like for high-rise buildings. Panel zone is given. So between the floor, panel zone is there. So between the beams, panel is created. And deformation of the panel will give you the deformation of the building that way. The panel zone deformation also is considered. So everything is manually calculated. You go one by one. What I explained today for P delta effect, other things you need to apply. Again, sigma V, sigma I upon L, Ig upon Lg, sigma Ic upon H. These are the girder. This is for the column. And I'm obtaining this bent displacement. And after that, sigma P, and again the bend displacement. So calculation of shear leak, story drift, and lateral displacement. So I will apply the formula. So now bend displacement has changed from 6.8 inches So this is due to the story leak, how much the displacement has happened, plus this. So this is all in higher requirements. You have to understand, but minimum you have to do is for P delta, what I showed you for P delta analysis, that is more critical. However, this document has many other things that you should know in analysis of the high-rise buildings or the tall buildings, which are related by drift. So drift design of the frame shear wall systems, this is very critical. And I don't think we will be able to cover this today. So maybe you go through it, and next session we will also take your doubts on this particular topic, in which drift design of the shear frame and shear wall systems are there. However, let me just show you the main thing. Now, Fazlur Khan and others estimated the lateral displacement at top of the 30-story frame shear wall building. So you are the originator of the system. Assume a uniform lateral pressure of 30 psf. Story heights are 12.5 feet. Use gross concrete section properties, and E is this. Now this is the column C1, C2, C3, C4. Column types are there. Size is given. Moment of inertia is given. I by L is given. So total I by L is equals to 4 into 0.1067 plus 6 into 0.1976 plus 4 into, so at each story how many columns are there that they have added, and you will get I by L, total I by L. So there are 1, 2, 3, 4, 4 here, 1, 2, 3 here, 1, 2, 3 here, 1, 2, 3, 4 here. Okay, So that way you can estimate how many numbers are there and how much I by L you have per story. Now you are getting a moment of inertia of beam BD cube by 12. Okay. So B1, B2, B3, like this is B1. This is also B1. Okay. So, and this is B2. Inside this B2 is given. And this is B3. So all moment of inertia you have obtained, total I by L you will also get from numbers. So I by L for columns, I by L for beams, and I of the shear wall is also BD cube by 12. So 2 into 28 cube by 12. So this is total is 28. 2 into 28 cube by 12. And you get I by L of this particular. So 2 times of this. So 2 columns are there. 2 shear walls are there. Now SS upon SC is your I by L divided by 4. So this formula from where it is given. So shear wall is SS. Sum of the stiffness of the beam is SB. Sum of the stiffness of the column is SC. Sum of the stiffness of the shear walls is SS. So sum of shear wall upon column stiffness. Sum of the column upon beam stiffness ratio. Free deflection of the wall is let's say 30 into 4 into 24. So this was the cantilever. What is the displacement of the wall? Now delta is equals to WL4 upon ATI. So that is already we know that this formula exists for the shear walls. Based on that formula, you are giving this inches and using the curve corresponding to SS upon SC equal to 20 from chart A. So you have to refer the book of Mr. Smith, Dr. Smith, Stafford Smith, in which the graphs are given, and from those graphs you can estimate the displacement of the building and get a graph something like this. So level and displacement you will get from that particular graph for the frame and shear wall building. Okay. So for simple buildings, you can get all these answers. For more complicated, you have to work more. And so first you go through all these, this aspects which are mentioned in this handbook by Dr. Farzad Naeem. So he's an influential person, and the softwares are all made based on his and his colleague who have worked on ETABS to give the solution. So that's why I'm showing you these problems, because these problems are all initial problems in which the ETABS, all problems are confirmed with respect to that, and the solution is matching to the ETABS problem. So if you are able to solve in this particular way, you should also be able to do your particular problem, which may match with the software. So various other references are there that you can go through. Now I'll just take this method, iterative method. So any, first order, second order base shear, how to estimate it, that I had explained you. So first you take a first order in which the column is straight, you analyze it, find displacement, story drift. Then you give a delta first order, find the, first order iteration in which you get V1, T2 and delta 2. Then you make second iteration in which you get D3 delta 3 and V3. And when the results of the displacement in the iteration 1, iteration 2 are 0.001 or 0.01, you can terminate the analysis. Here it is 0.01 has been taken as the measure to terminate the analysis. So this also you can put it in the software, or you can see what software is using and then you can judge from it. So this is the model that I received from Akhilesh for that building that I had shared. You can create only one model, no need to create a full two building model. So if you want to do a common podium building analysis, then it is okay. Otherwise, you make only one model along with podium. So what is the procedure? You model one building with the podium and submit the results. You don't have to model both the buildings for the submission. And the design for this building, if it is similar to the other building, then no need to model this building. So if everything of building 1 is equal to everything of building 2, same, then no need to model two buildings. If there is a difference in the geometry or the properties or the sizes, then you have to model both buildings. Otherwise, you model one building with podium, and if this building is separate, then you create another model in which this building and podium is there. Take the worst case. Then you create a common multi building with podium model for overall stability check for submission to the authorities. So this is how it works in the analysis and design of the high-rise buildings. So one building with podium, second building with podium, whatever is the worst case in design, you take it for the podium. Building each above the podium, independent design you will do, and combined analysis for both the buildings for podium also you will carry out if there is a backstay effect. Okay, so substructure, superstructure analysis, both you will conduct, combined and separate. So any query into this, then okay, so I'll first show you this P delta options. So once you have given the mass source, you have defined the load patterns and you have defined the load cases. Now you can go to P delta options. Now non-iterative based on mass you can select, or iterative based on loads you can select. So always go by iterative method. So 1.2 of the dead load. If there is a super dead load, then also 1.2, 0.5 of the live load, and all dead load, all live load you have to specify here. So dead load, super dead load, live load. So that this way you have to specify. Now you can see the convergent tolerance is 0.0001. So the software will run the iterations till the analysis meets what we say 0.01%. So what we saw in the document was 1%. Here it is 0.01%. Matching of the results is done by the software. So this way I will give it okay. So this is called preset P delta analysis. So this is P small delta you can see here. Okay. So this is for P small delta. So buckling of the column is covered into this part. Now second definition is in your load cases. So you can add a new case, and here you see in every load case that you do, now they will ask you preset P delta, do you want to use it or not? So that's why once you click it, it will take the deformed position of the building, that is from initial vertical position, the column is shifted to another position. And after that, the analysis, all loads are applied onto it. So that way it will take the second order effect from here. Or you can use nonlinear case load at end of, so nonlinear case, you have to specify that way. But we always prefer initial preset P delta option. So in this, you can also go with the, you know, non-linear static with the mass source. And so what all you can do is go to the load combinations, add new combination, default combination for concrete frame design. Now you convert to nonlinear load cases. Okay. Right. What will happen? This nonlinear load case will take into picture the P delta option, and you again go to this. Think when you modify or show this option. So here P delta is selected. Geometric nonlinear option is selected in this. Previously it was not there, but now it is converted to nonlinear. So P delta is considered here. Okay, so nonlinear static considered in load cases that was recently added. So previously there was only 3 load cases. Now once I converted the load combinations into nonlinear load cases, it has load combinations has come into load cases nonlinear, in which P delta is available. There are 2 ways to do it. So what I would say is delete. Okay. And here you can see that preset P delta option is there always. Then you don't have to do in the load combination. So preset P delta from here, you define it and it will do the P delta analysis for you. So what you have to do is you have to make a building, and first you do the analysis without P delta. So you don't define this option P delta. Find out the displacement, base shear, and story drift in Excel, and then you do the analysis in ETABS with P delta. That is, you define P delta now, 1.2 dead load, live load, and with respect to that, you check what is the increase in the base shear and the displacement and the drift, and try to reduce the what we say, try to increase the accuracy by the method that Farzad Naeem has explained to you. So I just wanted to ask you, is it clear that this method is simple and easy to follow, or you need more explanation on this method to follow? So will you be able to do this for a problem in ETAM, that without P delta, with P delta, what are the change in base reactions, also story shear, also your displacement and drift, and with P delta, story shear, displacement, drift, and base shear, what are the changes?
Sir, I have some questions. And in
Yeah,
ETAP, sir, I can do that. But sir, what we exactly mean by convergence sir, in P delta?
exactly mean by
Convergence.
convergence is like trial 1 and trial 2. There should not be much variation in the result, like 1%. So if my answer is 0. Let's say 4.24, and I am getting 4.25. Okay, in the next iteration. So first iteration I got 4.24, second iteration I got 4.25. By 1%, that means both analysis meets, and I will not do any further accuracy increase, and I will stop the analysis. So 0.01 tolerance limit I achieved. So my inaccuracy is 0.01 in the analysis iteration 1 to iteration 2. So at that point I should stop. Now if my answer is 4.244 and I have got 4.25, okay, and I have said that my accuracy is 0.001, okay, then this will not match. So 4.424, then your answer should be 4.425. So last digit 0.001 matching happens, then the analysis will stop. So either 100 runs more you will do by taking 0.001, or you will make it 10 runs more you will do, or you will make it 0.01 or 0.001. So what is your tolerance limit? How much accurate you want to be? that you have to justify. So for manual, 0.01 is good enough. You should not go beyond that. So that much accuracy or convergence you should keep in the analysis from iteration 1 to iteration 2.
Okay, sir. And so, sir, for P delta, sir, we have to depend only on software, or we can do it manually.
I showed you, you can do it manually.
For the tolerance of 0.01.
You can increase also. Now manually, that means you can do in MATLAB also. No need to, or in Excel also you can take that. But how many runs you want to do, that will depend how much effort you are putting. But 0.01 is the minimum you should keep.
Okay.
Beyond that, it is up to you how much you want to increase. So if you go into MATLAB, you can put any iteration numbers, it will automatically calculate. But in Excel, you will have to do it every time. You have to repeat the procedure every time, and either you have to go to VBA, in which you will put that iteration that way.
So there is any measure, sir, how we know that we are doing it correctly? Is there any measure of that?
I'm not able to hear you clearly.
So is there any like measure of that value, like we are getting the value? How can we know that it's a correct value, sir?
How can you know which value?
How can we know that the value we are getting in P delta is correct or not? Is there any method for that we can correlate with it?
Means cross-checking the results.
Yes, sir. Yes.
There is, I think, no such cross-check. It is just you have to obtain the displacement and just keep on adding it.
Okay.
So there is no cross measure to this method. Only what has been given the formulas, you have to keep on applying because it is a linear method. So you can see, I told you that force increased by 5%, so displacement increased by 6%. So in the linear, force and displacement are linearly proportional to each other. So that way also you can see that my 5% increase in the force is there. So 2% increase in displacement is not possible. So it has to be round about 5 or 6% increase in the displacement. So that linear approach, you can just validate it.
Okay,
As such,
sir.
will never happen this way. It will always give you the right answer because it is elastically added.
Okay.
Yeah, so I'll share this model in the MS Teams also what Akhilesh has made. So others can also improve this model and also give the section sizes, and on section sizes of the ground floor only to be provided, because rest all you can optimize later. For creating the model, ground floor size you generate for the columns and the beams, and you can take it multiply it on all floors. Okay, select all columns and beams and replicate on all the floors. That is not a problem. So that will not take you more than half an hour to do. Okay, so once you have done with the ground floor, you just have to replicate it. So modeling ground floor will take you 20 minutes and replicating it will take you 10 minutes. So if you are free today, I would suggest you complete the modeling if the grid dimensions are also there, and you model for one building, not both buildings, and also model the flow diaphragms, rigid diaphragm of 150 thick, and semi-rigid diaphragm so there is here it is not semi-rigid, so you give rigid diaphragm and give the stiffness modifiers to the diaphragm, beams and columns that way. And using my section lecture number 6, you can do the response spectrum analysis, and also you can do the P delta analysis if required. So there is a 7-story building also that I had uploaded. It is a simple building in which you can check. It is very symmetric, very simple frame. This frame we can do it for the higher analysis. Yet this model is not yet ready, so you use previous model which I had shared with you for doing the analysis. So apply the loads, dead load, live load, whatever you want to apply. And based on, so whatever that means, there is a right now for this exercise, you can do that. However, for a real building, whatever the loads are coming, we have to apply those loads accurately. So let me see if I can open another model. So I'll just show you the model which we just completed. It is a heavy model, so it will take some time to open. So you should have at least 16 to 32 GB RAM to have good graphics and good analysis time or runtime, uh, less analysis runtime. So is my model visible to you?
Yes, sir.
So these are two buildings. However, the buildings are same. Only one building with podium is modeled. It is below. There are 4 floors. Okay. So this way it has been modeled. So above there is a OHT and also some rooms are there. So 2 floors you can see above. And also solar panels are on top of this building. And there are many shear walls and columns. So columns are gravity columns and there is a central core. Rigid core is there. And perimeter beam, it is bounded by that. So this plus arrangement of the building you will see mostly everywhere in Mumbai, where this type of buildings are uh, there, mostly I-shaped building. And it gives a very strong core at the center, and perimeter is to be very well connected by the columns. So they take the lateral forces. Inside all are the gravity columns. Now, if we look into the P delta option, they have not yet defined here. And load patterns. So there are dead and live is general, super dead load, mechanical is live load, that is the lift load, then non-reducible live load, then so various wall loads are there. So wall 6, wall 7, number wise it has been given, right? So various wall loads are given. So this is the wind loads on coming onto the walls. So these are all wind loads in different patterns are applied. So wind in X, wind in Y, this is additional requirements, user loads, not defined loads. So earthquake load is defined. However, the wind load has been defined by them in a different way. So you can estimate and also apply it here. X and Y direction, then different cases are generated based on your requirement. Temperature, wind load up and down, then this is the reducible live load. This is what we say that some collateral loads are also there. Temperature plus minus temperature effect. So there is another structure due, so that structure's wind load is also applied to this building. So between the two buildings, there is an additional structure. On that also wind is coming. So that's those wind loads are estimated separately and applied onto the building. And this is no load generated, which is just mentioned here. So fine load. So this has just some error in which there was some application from the given requirement. So temperature load is also applied here, this particular case. Construction load, all those, whatever the loads are coming, overhead water tank, then on the stilt floor, there is a fire tank. So all those loads are applied at each floor wherever it is required. And from that you can load and live load. So you can see everywhere 2 kilonewton per meter square live load is there. Super dead load is 4.45. So this is 3.5. So waterproofing and all those loads has been estimated. Then mechanical is I think mechanical load is not yet applied. You can see this is the lift load, in which lift load they have taken as 3 kilonewton per meter square. So based on that also there are different loads that are coming. Maybe 10 kilonewton per meter square also may come. So after getting the real loading, you can also apply, or you can take 10 kilonewton per meter square for the lift area. So this is the podium level. You can see these loads are 20 kilonewton per meter square. That is non-reducible live load is I think a parking load. Then there is a super dead load 10.5 and temperature change 20 degrees Celsius. So all loads are applied onto the floor. So tower area, non-tower area, the loads are that way given. So this is on the podium top. Below the podium, there is no such load. So if we see the live load again, so again it is 2.5 and 3 kilometer per meter square maximum applied. And super dead load of 2.25 kilonewton per meter square below floors. Now from this you can see that your XY axis is here and the model is created. Some part is on other side of XY as well. So when you estimate CM and CR, all those things, you have to be sure that what you are doing. So these two building models below the podium, it has been modeled same. However, above the podium, the model for both the buildings is not made. So this is the tower area. And this starts the podium level, where it is connected at one floor above ground. And there is a swimming pool in the white portion here. Above that, below that, there is a parking. Okay, so that way. Okay. And here, if you define P delta of, let's say, don't define, then we go to those combinations. So this additional loads are generated. Let's see. So there is no preset P delta option considered here. So here it is none. In this, the P delta analysis is not considered in this particular model. However, the final model has considered this results as well. So this way you can do with P delta and without P delta analysis. So any query into this, what we have covered today for P delta analysis, why it is important and how to estimate it and how to do it in software. Also manually you can do it, in which you have the axial force P in gravity analysis using beam reaction method. Then you have lateral force using the this static equivalent method. You can estimate the lateral force. For this frame, you will get the P and V. And after that, you can estimate the linear displacement at each floor using the approximate method textbook I have given you of Scarlett. In that, you can estimate the story displacement manually for the entire frame. And after estimating the displacement and drift, you can apply the formula of Farhad-Naim and obtain the second order shear, displacement and drift, and continue with that. So how to estimate manually is given in Scarlett book. Also, if you are not able to understand, you can let me know during this week. However, first try in ETABS if you are comfortable with it. And then you give the dead load, live load, super dead load, tank load, whatever load you want to give, what is coming into your facility. Then without P delta, with P delta, you just confirm the changes in the results in tabular format, either in Excel or whatever way you find it suitable to do it. Okay, so that is what I expect for this week. For that, whatever I have discussed with you for this particular table should be understood by you. Like this linear first order analysis. This is second order first iteration, second iteration. The difference is only 1%, 0.01 difference between the results. And then you terminate the result and compare it with the software also. That is what you can do. So you can take this table from the software without P delta. You generate these two tables and then do P delta analysis in the software and compare the results. So it is a simple task, not much big task. 1.2 dead load, 0.5 live load. You have to apply in the preset P delta option in ETABS. Right? So my task was to make you aware on how it is estimated and why it is estimated. So how and why is covered and what difference is coming, you can share with me in this week. And also complete the model for the 15-story building that I have given. 7-story model that I have given, you can use this for P delta analysis. Okay.
Okay.
So any query on today's session on stability analysis of the building using drift limitations? Okay, then. So we'll connect during the week also, because this is critical topic. So I want you to estimate in Excel sheet for this 7-story building at least, or any building that you want. You can also try 3-story building, then 7-story building. In which cases this has become significant, you will come to know. So for 3-story building, is P delta significant or not? For 10-story building, it is significant or not? For 30-story, how much it is significant? That way you will be able to understand. Okay, so this is important part where P delta analysis becomes critical. Okay, so that is there for today. Thank you for attending. Be connected on Teams and WhatsApp and share your queries and also your results next Saturday.
Thank you, sir.
Okay. Bye.